Hello everyone, this is Dr. Lennon, and today we're going to be talking about sequences. Sequences really we're looking at kind of with an idea of moving towards series. So what a sequence is just an ordered list of numbers. So a sequence is an ordered list of numbers and usually we'll use the notation. We'll have braces, and then we'll have a letter with some indices indicating which term we're talking about. And these can start anywhere, so you can have some indices maybe going from n equals 1 up to some larger number k, if it's finite, or let me get rid of that comma. Or it could also be infinite. So, you could have, say, an going from n equals 1 all the way up to infinity. So that's one thing. The list can be either finite or infinite. So the infinite ones are a little more interesting for us because we can start talking about concepts such as limits of the sequence if they approach some number. Related to these, and it is important to note that the list has a specific order, but we can also talk about an infinite series or a finite series. So a series is a sum of an ordered list of numbers. So as we'll see, these two things are intimately related. We can always think about sequences or series as partial sums of sequences. So again, we'll use the capital sigma notation to talk about that sum. So say if we had a finite list, we could look at the sum from n equals 1 to k of a sub n, right? And this would just be basically a sub 1 plus a sub 2, and all the way until you get to that last value, a sub k. And if it were infinite, the sum would just go on and on and on. So if you had an infinite sum, this sum would continue ad infinitum. So it would just keep going on and on and on. And just because you're adding an infinite set of values, that does not necessarily mean that it would have to diverge to infinity. It can converge even though it goes on forever. So we'll talk about ways to test for that convergence or divergence. It's actually quite simple for a series. So we'll learn lots of different tests for that. So also we can talk about a sequence of, for any sequence, we can talk about its series of partial sums kind of as a running total. So given let's say an infinite sequence, a sub n going from, say, n equals 1 to infinity, we can associate to it a sequence of partial sums. So the sequence of partial sums, let's say we'll denote with a bunch of capital S's with indices, S sub 1, S sub 2, S sub 3, and so on. And what are each of those capital S's? So where we can say S sub n is just the total of s sub 1, s sub 2, until you get all the way up to s sub n. So for instance, s sub 3 would be, oh, sorry, I'm adding the s's. I meant to be adding a's there. So those should not be s's. The s sub n is the sum of all the a's up to that indice. So this would be a sub 1 plus a sub 2 plus a sub 3 and so on until you get up to a sub n. So if you were looking at a sub 3, or s sub 3 in particular, that would be a sub 1 plus a sub 2 plus a sub 3. Okay, so let's look at some specific sequences and kind of understand what they're going to. Let's briefly just talk about what a limit would mean, and then we can look at some sequences and see whether or not those limits exist. So definition. If the terms of a sequence approach a unique number L as n increases, so basically we'll say that is if a sub n gets arbitrarily close to L as n gets sufficiently large Again, if we were writing some more proofs in this class, we could talk about this in a more precise way using some epsilon delta notation, but we're just going to kind of wave our hands and talk about getting sufficiently close. That means if you give me some number, I can always take n larger such that my sequence will get closer to that 2L than that boundary number that you've given me. So if this happens, we say the limit of a sub n as n goes to infinity is in fact L. So we say a sub n converges to L. Or the limit as n goes to infinity of a sub n is equal to L. So again, this is just from n equals 1 to infinity, the sequence. If no such number exists, or no such L exists, we say that the terms of the sequence don't converge, or we say the sequence diverges. So let's look at some just simple examples where we can talk about the limit. Example, determine the limit of the sequence, or say it diverges. So let's look at a few. So the first one, let's look at, I don't know, a very simple one. 1 over n as n goes from 1 to infinity. So what does the sequence look like? The sequence just looks like 1, 1/2, 1/3, 1/4, and so on. So the numbers get smaller and smaller, and we know from taking limits that if you do the limit of 1 over n as n goes to infinity, this limit equals 0. So basically the limit here as n goes to infinity of 1 over n is just equal to 0. So pretty straightforward there. What about if we did something like negative 1 raised to the n power? We look at this sequence as n goes from 1 to infinity. Well, powers of negative 1 we know are either going to be negative 1 or positive 1. And we're starting with an odd power, so basically this sequence looks like negative 1, positive 1, negative 1, positive 1, and so on. The terms just keep alternating, so you're never getting very close to any number, right? You can never get within 0.1 of a half, let's say. So since we can't get arbitrarily close to something, we know that this limit is diverging. So the sequence diverges. So a lot of times when you see things bouncing from positive numbers to negative numbers forever, they're going to be, sometimes they're going to be diverging. We could combine the two if we looked at negative 1 to the n over n. That sequence would be alternating, but it would still be getting closer and closer to 0. So it would not be divergent in that case. It would actually be convergent. So we'll look at a number of examples. Well, let's do one more, something that doesn't converge to, say, 0 or diverge. Let's look at the sequence of, say, let's say, I don't know, 4n squared plus 1 over 3n squared minus n, as n goes from 1 to infinity. Now, again, this just goes back to looking at the limit of a rational expression where we're just looking at the dominating terms. We also recently did L'Hopital's rule, so we could use L'Hopital's rule for this. But again, these terms are going to be looking term by term. We're going to look a little more confusing, but we know if we looked at the limit of this closed form here, that's all we have to look at is essentially the dominating terms, so the coefficient of 4n squared and the coefficient of the 3n squared are all that matters, so this limit goes to 4 over 3. So that would be the limit of our sequence there. As the numbers get larger, the plus 1 on top and the minus n on bottom become significantly less important. So let's go ahead and talk about some other terminology. So some additional terminology. So we say a sequence A sub n is increasing, which I'll just abbreviate INC period, if your successive terms are always greater than your previous terms. So A sub n plus 1 must always be greater than A sub n. And analogously for decreasing. But if we said it's non-decreasing, then that's going to change that strict equality to a greater than or equal to. So A sub n plus 1 must be greater than or equal to A sub n. So the terms could be getting larger or they could be staying the same, but they just couldn't be getting smaller. So again, decreasing, A sub n is decreasing if A sub n plus 1 is less than A sub n, and it's going to be non-increasing if we have that non-strict equality, so less than or equal to A sub n here. Okay. So we also talk about monotone or monotonic. So we would say the sequence A sub n is monotonic if it is either non-increasing or non-decreasing. So it's only moving in one direction. It can't have part of the sequence that's increasing, part of the sequence that's decreasing. We're talking about the entire thing has to be moving in one direction. So it's either non-increasing or non-decreasing. So moves in only one direction. Because you can talk about certain subsets of a sequence as being increasing or decreasing or non-increasing or non-decreasing. You can also talk about a sequence being bounded. So that means all the terms have to either be greater than or smaller than a specific number, whether you're talking about bounded above or bounded below. So an is bounded above if there exists a number m, capital M, let's say, such that a sub n is less than or equal to m for all n. And we could say it's bounded below if there is m such that they're all so it's bounded below if there exists a number m such that a sub n is greater than or equal to m for all n. All right. If it's bounded on both sides, we would say the sequence is bounded. So you could be bounded above and also bounded below. All right, so let's talk about some geometric sequences. So a specific kind of sequence where all the terms are related by being multiplicative multiples. So definition, a geometric sequence have the property that consecutive terms are obtained by multiplying by a fixed number. Usually this is denoted by R, which is known as the common ratio. So a geometric series, or sequence rather, excuse me. So it will have the form either r to the n, or it might start with some initial value a being multiplied by r to the n. So, you know, just an example, you might have, say 2 to the n equals 1 to infinity. So this would be a divergent sequence that goes 2, 4, 8, 16, just doubles every time. Another one, maybe we could have something like let's say 7 times 1/3 to the n. So this is a sequence that's going to 0, but would start with 7/3, then 7/9, and so on. So those would both be geometric sequences. And geometric sequences are going to be very nice because we can always tell their limits very easily. So it's either going to go to 1, 0, or will not exist. So this is kind of a theorem that is not so hard to prove and should be pretty obvious to you. So if r is a real number, there's only a few possibilities for the limit of a geometric sequence. And soon we'll see that these are nice for infinite series as well, because we can find their limits quite easily too. So it will go to 0 if the absolute value of r is less than 1. So if you're multiplying by something less than 1, it's going to continue to get smaller and smaller and smaller and will eventually go 0. It'll be 1. That only happens if r is equal to 1. And it will not exist if, let's say, r is less than or equal to -1, or r happens to be greater than 1. So basically, if the absolute value of r is greater than 1, see, there's a little problem. It will converge if it's 1, but it'll diverge if it's -1. So you're a little bit different on that point, because as we saw earlier, the -1 to the n series will alternate between -1 and +1. Really, in terms of sequences, this is pretty much all we want to say. Yeah, this is pretty much the basics of sequences, and really we're going to use this moving forward to talk about series. So why don't we look maybe at a couple other limits of sequences as an example, but other than that, really not too much else to say. The geometric ones will come back to us when we look at the limits of series, which are going to be much more interesting. So again, we'll look at find the limit of each sequence, or yeah. So let's say, I don't know, we have the, so if we don't have any limits on the outside, just assume it's going from 1 to infinity. A lot of times kind of those will be left off. Let's say we have 3 to the n plus 1 plus 3 over 3 to the n. Okay, so again, we're just looking at the limit of the closed form here. So the limit as n goes to infinity of 3 to the n plus 1 plus 3 over 3 to the n. Well, essentially that plus 3 on the top doesn't really matter for us. So this is just going to be the limit as n goes to infinity of, say, 3 to the n plus 1 over 3 to the n. And we know that this can be actually written as, say, the limit as n goes to infinity of 3 times 3 to the n over 3 to the n. So really, those cancel, and we see that our limit here is just going to be evaluating to 3. So that would be the limit of this sequence. Again, just kind of focusing on the dominant terms. Let's go ahead and look at maybe the sequence where we look at n plus 1 factorial over n factorial. So we'll talk about something called the ratio test in when we start talking about the convergence and divergence of series. So again, remember the factorial is just multiplying by all the integers less than that number until you get down to 1. So again, we can actually rewrite this by looking at n plus 1 factorial is actually just n plus 1 times n factorial over n factorial. And then because these cancel, we're actually just looking at the limit as n goes to infinity of n plus 1, which we can quickly see diverges. So this diverges. That limit goes to infinity, so it's not approaching any finite number. Okay, so why don't we try maybe one or two more. Just, again, this is helping us brush up on our old limits here. So what if we looked at, let's say, the inverse tangent of n? So when I think about this one, I'm more likely to think about the graph than thinking about the actual limit. So we want to know the limit as n goes to infinity of the inverse tangent of n. So I think about the picture. So the picture here, if you look at the inverse tangent graph, remember it's the principal value region, and we're just looking at kind of the reflection about the line y equals x through the principal value region. So we know the inverse tangent graph actually looks like this, where we have two asymptotes, one at negative pi over 2 and one at pi over 2. So we can see as we're moving to the right, as our input values are getting larger and larger, we're actually just moving toward pi over 2. So there's one that you can kind of approach with a graphical argument. So that's going to be our limit there. And then maybe we'll do one. Let's see if we can mess around with some exponents some more. Let's look at the sequence e to the n over 10 over 2 to the n. Again, this one's not so bad. We just need to remember some of our rules of exponents. So if we're looking at the limit as n goes to infinity of this quantity e to the n over 10 over 2 to the n, this is really just the limit as n goes to infinity of, since they both have n's, we can actually pull that n out. So it's going to be e to the 1 over 10, or the 10th root of e over 2, with all of that being raised to the n. So then what we care about is, this is, now that we're looking at it, just a geometric sequence, right? So we have to ask ourselves, is that geometric sequence e to the 1 over 10 over 2, is that bigger than 1 or smaller than 1, or equal to 1? Well, we know e is about 2.718, so the 10th root of e is going to be less than 2. So this is going to be equal to 0, basically by geometric series, or geometric sequence, excuse me, that theorem that we just talked about, since e to the 1 over 10 over 2 is less than 1. So that's why we know that goes to 0. So that makes use of that last theorem we talked about. So that's it for sequences. So we'll move on and begin talking about infinite series next. And that again is going to be more to the point of what we're going to be doing for the rest of this class, moving towards Taylor polynomials and things like that. This is Dr. Lennon signing off.